Welcome to Calculus. Today we will investigate function continuity, focusing on solving for our constant value to create a continuous piecewise function. Let's take a look at a total of 5 examples. We'll see 2 to begin and then we'll conclude with 3. Let's head over to our notes screen. So our first function is here, this piecewise function f of x equals, in one case, x squared, and that's when x is less than or equal to 3. And when x is greater than 3, it passes over to this linear function ax. So for sure, our first goal is to solve for that a. A is a constant, some number. Our goal is to find the value of a that would make this piecewise function continuous. So let's begin by just noting that this is really 2 parts, and we're going to say that the first one is f of x equals x squared, and that the second one is also f of x, but ax. Now, the thing we need to note is that we've got x values, and then we're going to use the idea of y values that are the same. And that's really based on the task that we're trying to do. We're trying to make these 2 kind of disparate functions join into one. And so really where we'll start is the common x value. So the common x value for these 2 functions is the place where they change over one function to the next. So for us, that's given here as 3. So what I want to do is I want to calculate first to begin is f at 3. So I'm going to clear that out. And really, we're going to replace the x's with that 3 as well. So f at 3 for the quadratic will be 3 squared. F at 3 for the linear function is just a times 3. Well, we can simplify that. So for the quadratic, that just gives us 9. And for this linear, we're going to say that that's 3a. So our first step was just find that common x value, plug it into the function, into both parts of the piecewise function. Now, the second step is really for us to match up the y values. If we can match up, we've already matched up the x values, they're both 3. If we can also match up the y values, that would ensure that they're meeting and the 2 parts of this piecewise function are creating a continuous whole. Now, that idea is really right in front of us. So if I know that f at 3 for one is 9, and that f at 3 is 3a for the other, to make sure that they match up, I just need to set these 2, really those are y values. If I set those equal and solve for a, then I should be good. So I'm going to say that 9 equals 3a. And then I want to solve, so I'm going to divide both sides by 3. And we get this function where a equals 9 divided by 3, or 3. So I'm going to box that because that really is that first task. I want to find the constant a so that the function is continuous on the entire real number line. And just to recap, the way that we did that was we took the common x value, substituted it in to both functions, and then once I evaluated, those are y values because they're outputs, set those equal and solve for a. Well, the proof is in the graph, really. So where I'm going to head now is to graph this piecewise function. And my hope is that with the a value of 3, that the 2 functions meet up, both at the same x value and the same y value. So I'm going to create a table of values here. And because it's a piecewise function, I'm going to make it 3 columns broad. So our x values will be here. So we definitely want to graph this, but I'm going to center it. Really, I need to at least include positive 3, the common x value, and then x values on either side. So we'll start with -2 so we get a good snapshot of the quadratic. And then we'll go all the way through, let's go through 5. So the threshold value is there at 3. And what we'll be looking for is that the y values are the same. If they are the same, that means that the two functions have matched up and there's a nice continuity across that divide. Well, let's check. So my first function is x squared. So I'm going to substitute in -2 for x squared, and that's the value of 4. So you'll recognize this first function as the quadratic parent function. So -1 squared is +1. 0 squared is 0. And then here we're going to see this symmetry that's real characteristic of the quadratic function. 1 squared is 1. So notice those values are mirrored or echoed across the origin. We see the same thing for +2. +2 squared is 4. All right, let's also evaluate at 3. So at 3, that's 9. So I can graph that now. So over here, I'm going to graph the point -2, +4. -1, +1, 0, 0, 1, 1, 2, 4. So you can see that symmetry that we saw in the table shows up in the graph as well. Those points are symmetric across the y-axis. And then 9 is above the graph. So I'm going to just estimate that 9 is about there. And then 3, 9 is here. So I'm going to sketch that quadratic parent function. So it kind of descends from this left side and then ascends up to that value. Now the left side takes the arrow. The right side, should that take the arrow? Or should it be truncated right there at 3, 9? Good. Yeah, it's a piecewise function. So I'm going to leave this right-hand side as a firm, just kind of a halt. And at that point, 3, we're switching over to our second function. So that's this ax. Now we had defined a as 3. That's what we solved for here at the outset. So I'm going to put instead of ax, 3x. Where I'm going to begin is at the cutoff for the domain. So at 3, this is going to be 3 times 3, which is 9. Now that's a good sign because if we compare our y values at that threshold, they're the same. Let's keep calculating a few values. So this is 3 times 4, which is 12. Way off my graph, but that's just fine. It's just a steep line at that point. And then 3 times x value of 5 is 15. Well, I'm going to graph this. So keep in mind this ax part, it's strictly greater than 3. So it doesn't actually have an x value of 3. It does have the x value of 3.000001. Anything close to 3, greater than 3. So I'm going to kind of mark something there to the right. And then at 4, we've got the value of 12. So I'm going to count up 10, 11, 12. So we're kind of stealing from the words right now. And 15's way off my screen. So what I'll do is I'm just going to sketch this right side. Oh, we can do better than that. Okay, a little better. What the graph shows, though, is that our solution for a equals 3 works to make these two pieces kind of that could have been showing some kind of jump discontinuity totally continuous. The x values and the y values meet up. Let's take a look at a second example with a trigonometric function. So our task is exactly the same. We want to find a constant a value so that each function is continuous on the entire real number line. And then we'll prove it by graphing it. And we'll make that with a table of coordinate points. So let's start again as we did before, just by noticing what's the common x value. Well, if we look here at the way that the domain has been partitioned, the common x value is going to be 0. So as we did before, what I want to calculate at the outset is what is f at 0? We'll bring that over here to the right. So f at, let me put 0 here in a distinct color, we'll put red. For the sine function is sine of, let me put that place for the x. Instead of x, I'm going to put 0. And then there was an x in the denominator as well. And let's go ahead and evaluate that. And I think we see that we're going to have some trouble, because sine at 0 is 0. Just to recall the unit circle, that's where we define our sine, cosine, and tangent. The triangle, it's triangle at the x-axis, which is 0 radians, has a height of 0. So the y value is 0 and the radius is 1. So the sine value at 0 is 0 over 0, and that's a big problem. That's an indeterminate form. I've got 0 divided by 0. The numerator 0 is okay, but the denominator one is undefined. So I need to do something in a moment to see what is f at 0 for this trigonometric function. What's the y value when x equals 0? The algebra is not giving me a lot of information. Well, we'll head over to our graphing calculator. So what I'm going to do is I just want to look at the graph on Desmos.com and see if I can actually just graphically locate what is the y value of that sine of x over x when x equals 0. So I'm going to pull up the Desmos.com graphing calculator. And this turns out that this is a very useful function for us to investigate. We'll see in a moment. So sine of x over x. And if I create a table of values for that function, so we definitely see that this function at 0 is undefined. But if I look at the graph, and I can actually on Desmos kind of trace here. So if I start from the left and think about it like a left-hand limit, as I approach 0 in the x, the y value is getting closer and closer to what? I'm going to try to bring it real close. So negative 0.08 x value, the y value is 0.999. What's that getting close to? You can see right as I get, so at negative 0.04, it's at 1. And at 0, it's undefined. If I pass over to the right side, think about it as a right-hand limit, at 0.02, it's 1. So even though this function, sine of x over x, is undefined at 0, it really looks like it has the y value of 1. And if I put in that function, definitely I can see it there. It's attaining the value of 1 at the y-axis, even though at that very point it's undefined. So I'm going to head back to the note screen just with that in mind. Even though I algebraically can't calculate sine of x over x at the x value of 0, from the graph I can see that it has the value of 1. So right under here, it's kind of a tack-on note, but it's really equal to 1. And the idea is that the limit as x approaches 0 of sine of x over x equals 1. I'm going to go ahead and write that because that is something that we use quite frequently as we calculate limits of trig functions. So that's a true statement, and we just kind of have to accept it at this point. Now, that said, at this moment, what I can do is take the second part of the piecewise function, and I'm going to plug in 0 for the x. So I'm just going to leave a minus 3 there in the purple. And then the x value that we're looking at is 0 again, because that's the common x value. And just kind of cleaning that equation up, the negative 3 times 0, what is that going to become? Good, nothing. So what we get is that f at 0 for this linear function is just a. Well, I found the x values that were common. Remember, at this point, what we're saying is, okay, now I want to set the two y values equal to one another. And that is immediate. A equals 1. And without much further fuss or much further ado, we've completed that first task. A is 1. Well, let's graph. So I'm going to create the coordinate plane graph over here. Let's make our coordinate table. And like we did for that first example, I'm going to place 3 columns broad. And let's go -3, -2, -1. That cutoff number is 0, and then let's go 1 and 2. Well, we'll go to 3. We'll be generous with the x values. So first, let's calculate sine of x over x. Now, that's kind of cumbersome to calculate. So what I'm going to do is I just want to head back over to the table over here on Desmos, and I'm going to record those values from that table. And what we'll do before I head over, let's finalize the equation for this linear one, and let's place that in our third column here. So that's a minus 3x, and again, we'd solved a as 1, so that's going to be 1 minus 3x. So I want to create that table, 1 minus 3x and sine of x over x. And let's get those values. So we'd kind of looked at the sine of x over x already just to see what's its value at 0. I think we're good without that line now. So I'm going to record here. So at -2, the value is about 0.45. At -1, it's 0.84. At 0, it's undefined like we saw. But I'm going to put in parentheses 1. All right. So that's good. We can calculate the linear function ourselves. So I'm going to head back to the graph and just fill in these values. I did not catch one for -3. Let me grab that very quickly. So I'm just going to hit enter here, -3. So almost right at the x-axis. So 0.0, about 5, basically 0. So back to the note screen, and we're going to graph this now. So I've got -3 as the output is 0.05. -2 had the value of 0.45. -1 was 0.84. Again, 0 itself was undefined, but we saw it had the limit value of 1. Let's calculate for the line. So 1 minus, we're going to start here at the common x value. 3 times 0 is 1 minus 0, or 1. So notice those y values match as we had created it here on the right. Then we'll substitute in x value of 1. So 1 minus 3 times 1 is -2. So definitely it's a negative slope. It's going down as the x values go up. 1 minus 3 times 2 is -5. And I see there's a pattern there in the descent. It's a constant descent of 3. So the next one should be -8. Well, let's graph these two and see if we got a nice continuous function. So -3 right here, 0.05. -2 is at 0.45, so right under half. -1's at 0.84. And then functionally, this is, I'm going to put an open circle at 1. Notice the first part is strictly less than. So really, we're not even saying that function goes to 0. So on the left, we've got this sine of x over x. And those ripples start to get kind of compressed both directions as you go away from the y-axis. Let's graph this other one. So definitely this other linear function attains the x value of 0 at 1. At +1, it's down at -2. At 2, it's down at -5. And then at 3, all the way at the lower part of our graph. And that completes our continuous piecewise function. So our a value of 1 does work there. Make sure that these two functions become continuous. Okay, so 2 examples of creating continuous functions by solving for a constant value. Thanks for joining for these 2 examples. We'll see a total of 5, so 3 more to come. But at this moment, let me let you go and work some of your own questions and then come back for an additional 3 examples. Thanks for joining. See you soon.